Seems like my mic was muted. Okay. Okay. So now it's visible, right? Audible. Okay, okay. Uh, all right. So, um, yeah, cool. Yeah, okay, fine. Right. So, okay, so hello and welcome everyone. Welcome to this lecture. Um, so, uh, so till now we have basically established some basic premises as to what we are going to do and what are the, uh, I mean, we have established some basic notation. We have established a basic, motivation that what is it that we want to do. And in the wake of those things, we also saw a very nice looking cute algorithm called expectation maximization algorithm, so called EM algorithm. And we saw in the last lecture, we basically saw that how is it that the EM algorithm helps us could be possibly used to um, you know uh, maximize your log likelihood and learn the and hence learn the underlying distribution and so on and so forth. Particularly the main uh, factor in all of those things was the introduction of a lower bound, which we called as evidence lower bound or elbow. And we saw that, I mean, basically it acts as a proxy to your log likelihood, right? Meaning that instead of maximizing the log likelihood, you are basically maximizing your uh, elbow. And one way to maximize that elbow was through the EM algorithm. And yeah, I mean, we saw how you could do that, and we saw some interpretations of EM algorithm. Particularly, we saw that you can interpret EM algorithm as first calculating an expectation, then maximizing it. However, a more intuitive explanation or understanding of EM algorithm is by looking at it as a double maximization or double maximization thing where you're first maximizing on your Q distribution or the variational distribution to maximize the uh, to maximize the uh, what do you call to basically maximize sorry to first step is to find a Q distribution that minimizes the KL divergence term in the elbow, which corresponds to setting Q of the Q distribution to be equal to the posterior PZ given X. And then the second step corresponds to maximizing the elbow for this particular Q distribution, right? So let me share my screen. I'll just shortly recap that thing. Right. So I hope the screen is visible. Okay. Right. So, uh, okay. Cool. That's something I think can be done here. So let me just. Okay, fine. So, yeah. So this is where we were, right? So particularly we saw that, this was our elbow, right? I mean, particularly the elbow is this term, but right here. Uh, and yeah, I mean, we saw that, this elbow is what we will use instead of the log likelihood. So the elbow will put, in some sense, act as a proxy to your log likelihood, right? And yeah, I mean, we saw that end of the day, we want to maximize this elbow. And elbow is again a function of two things, the variational distribution, the Q distribution, and the parameters theta. So we resorted to a coordinate ascent kind of optimization algorithm, in which we first calculate this expectation term, which is again nothing but your elbow, but after filtering out the terms that don't depend on Z, right? Or sorry, theta. Yeah, so I mean, if the elbow is sum of these two terms, one is your expectation or this Q function, and the other one is your entropy. So the entropy is not dependent on theta, so we can just ignore that, and the Q is the one that we are interested in. So the first step involved maximization of this term, right? Which involves calculation of this expectation and setting Q of Z, your variation distribution, to be equal to P of Z given X. And the second step involves keeping this distribution as it is and just maximizing on theta. So the expectation and then maximization. So EM, like that, right? However, a more intuitive way to look at it is from this view where you have your elbow, right? Sorry, you have your log likelihood function, right? Log px, and you have your elbow and a KL divergence term, which constitute this log likelihood term, right? Uh, the E step is what you can look at E step as basically minimizing this thing, or in particular, you are increasing this increasing this elbow from this value to this value. It's like pulling this bar all the way till here, right? So this step is basically your E step, right? And then once you have done that, you are maximizing your Q function or elbow with respect to theta. So this is how the picture look like, right? So you have this is your, for example, log likelihood. You are at some theta old, right? The corresponding to different value of Q, right? You will have different elbows. So you are uh, first finding out the value of Q distribution, which maximizes the value of elbow for this given theta, which will look something like this, right? So this is like finding the curve corresponding to a given theta, which maximizes the value of elbow for that particular theta. So here the value of elbow is maximized for this theta, right? And once you have found such a curve, the next step is to basically keep this curve fixed and then optimize on theta and go from here to here in order to maximize this curve itself. You reach somewhere here. Then you again find another curve, something like this. And then you again go from change your theta from here to here and then again find maximize it. And I mean just keep alternating between the two steps. However, the main problem as we saw last time was uh, this this problem of getting computing pz given x, right? Which is generally intractable. What do we mean by intractable is that so pz given x is you can if you want to find it, you can write it in terms of Bayes rule, right? So this is p of x given z into p of z divided by p of x. So these two terms are fairly tractable. I mean, you can maybe you can use the PGM to find this term and you can set a prior or assume a prior and get the prior term. However, the problematic term is this P of X, which is intractable because P of X has this integral form, which is integral over Px(z) over all possible z's in some Euclidean space of some manifold. And hence this calculating this itself could be problematic, and I mean in some simpler cases it might be easier to compute. However, in case of more complex cases, yeah, this computing this distribution itself would be quite tedious, or or in some cases even intractable, right? So in those so that is the main bottleneck with EM algorithm, right? And so what is the solution, right? What do we do with it? So the solution is basically to, I mean, okay, we cannot set Q of Z to be exactly equal to this P of Z given X. So what we can do is we can restrict Q of Z to a class of distributions which are tractable. Okay. So maybe we'll see what we mean by that today. Okay. And this leads to a class of inference algorithm called variational inference, right? So let's look at it. Let's have a look at it. So, so this is number four. Right? So this is variational inference. Okay. So okay. Uh, so again from previous lecture, let's write down what the log of p of x was, right? So log p of x was this thing, right? Let's write it down again. However, we will omit theta here for the time being. I mean, uh, yeah, we will omit theta. We will remove this theta notation for the. I mean, you can think that theta is also a latent variable and it is subsumed in Z for the time being. But I mean, yeah, you will just ignore it for the time being. So, the main result is this thing, right? Right. ln p of So the main thing is that the log of p of x is nothing but your elbow plus a KL divergence dKL between Q and P. This is what we proved last time, right? This f function is your elbow, this is your KL divergence term, and this is your log likelihood. Nothing fancy, simple thing. So let's write down what is the problem with EM. The problem with EM was that uh, P of Z given X, computing this could be intractable due to intractable P of X. This was the sort of the main problem with the EM algorithm, and the solution to this problem is something called variational inference. And what does variational inference does? Like this is also called VI. So what does variational inference do? So variational inference basically what it does is, uh, okay, it's fine. So we cannot compute P of Z given X, and hence we cannot set Q of Z to be equal to P of Z given X. So point is difficult. So it's difficult to set Q of Z to be equal to P of Z given X, since P of Z given X is intractable, right? This is the main problem. Okay. So the solution is to restrict Q of Z to a class of tractable distributions, and then maximize the elbow. So this is sort of the main idea of your variational inference. That so we are basically saying that fine. I mean, like computing p of z given x is intractable, like difficult, and hence we cannot substitute q of z to be equal to p of z given x. So what do we do instead is we will restrict the uh, q of z to only take val to only take to only assume distributions which are tractable, okay? And after imposing that constraint, with keeping that constraint in our formulation, we will maximize our elbow. So that's the sort of that is where we are heading, okay? Okay. Uh, okay, fine. So I hope the premise is a little clear. Okay. So now let's see what so this lecture will basically have two parts. In first part we will just take one example from variational inference. I mean it won't be related to VAs or anything. I will just show you that how what do we mean by this particular thing, restricting Q of Z to a class of tractable distributions. We will uh, see something called now. In fact, immediately now we will see something called mean field approximation, and then after that we will sort of go on and see another kind of approximation that leads to VAE. Okay. So let's start with uh, something called this is called mean uh, this is called mean field approximation, or this is also called factorized approximation. So this is something that is apparently used a lot in physics. Okay, all right. So let's see what this is. Okay. So again, let us write down our elbow, right? So from last lecture, let us recall what was F. So your F of Q, uh, remember from last class, it was this thing, right? Integral of Q of Z log of P of X comma Z by Q of Z Pz. This is what our elbow looked like, right? As I said, we are omitting the thetas here. You can think that thetas are somehow subsumed in the latent variable Z itself. So we are not writing down theta here. Okay. In that case, here is the approximation, the factorized approximation. I will write it down. So factorized approximation. What is this? The factorized approximation tells us that uh, so uh, okay. So there are 2 points. So suppose partition we partition the elements elements of Z into disjoint disjoint groups uh, disjoint groups Zi uh, I going from 1 till let's say n. Okay, and the second thing is then assume that the Q distribution the Q distribution factorizes with respect to these groups so that what your Q of Z is equal to product of Qi of I going from 1 to n. Okay, this is your factorized approximation. So what do we mean by this? So we are basically saying, I mean, if I have to, I mean, remove the formalities, let's say Z is your a vector like this, right? It's a random vector which has, let's say, it's m cross 1. Okay, so there is Z1 all the way till Zm. You're saying that, okay, maybe what you can do is you can say that the joint distribution or the distribution of this random vector Z is nothing but just Qi of I going from 1 to m, something like this. This is how you are approximating your Q of Z. So remember, right? Uh, the whole idea of variational inference relies on this particular uh, constraint that we are going to restrict Q of Z to the class of tractable distribution that maximize and then maximize the elbow. So we have to do some sort of so I mean tractability per se is not something that you can mathematically uh, I mean write I mean tractability of a distribution is not something that you can explicitly write down in a mathematical equation, right? You will have to design a tractable distribution generally, right? I mean, you ha- you will have to come up with distribution which by design are tractable. And then you can go on and do other stuff, whatever you want to do. So the first hurdle itself is to, uh, come up with a distribution that is tractable by design or something like that. So here is one such approximation, right? So basically, what this thing is saying is that you have a m dimensional random vector, right? One way to come up with a potentially tractable distribution is to simply say that it is nothing but a product of its elements in the vector. I mean, this need not be exactly m cross 1. For example, you can club some of the vectors here, club some of the vectors here and here, and take the product of these groups and call it your joint distribution. That is what we mean that you are partitioning the elements of Z into disjoint groups. So there can be like uh, it need not be single element and then taking product of the distribution. It could be like you're taking clubbing a lot of vectors elements and then taking the product. That is also completely fine. So this is one example of how you can. This is one example of the said approximation, right? Okay. Uh, right. So let's see. Okay. I mean, this is So what are the implications of uh, such an approximation? So let's look at this. So okay, I mean, another thing to notice here is that we are not imposing any distributional constraint on these individual distributions, right? I mean, we are not saying what these individual distributions QIs should be. We are saying that, I mean, QIs could be anything. So, I mean, even though we are doing some sort of constraint, we are imposing some sort of constraint here. There is a lot of freehand here. I mean, we are saying that, QIs could be anything. So QIs could be a complex distribution, which we can perhaps exploit or use to finally maximize the elbow, right? So, I mean, I hope you can see that although we are assuming some constraints, we are still, we still have a lot of free hand to, do stuff. So let's maximize the elbow using this distribution, this under this setting, okay? And the way we will do is, any, I mean, you maximize the elbow, right? We want to do this thing. What we will do is we will do the maximization in turns, in the sense that there are these QIs, right? So there are these QIs that we want to maximize. So we want to first like find these QIs, right? What we will do is we will similar to the EM and not EM, exactly EM. What we will do is uh, 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 optimize with respect to these QIs in turn, meaning that we will keep so at a particular instant we will only optimize with respect to one I. Okay, for example, maybe let's say Q2. So when we are maximizing the elbow with respect to Q2, other QIs where I is not equal to 2 will remain constant. Okay, I mean we will not change them, and that is how we will maximize our elbow. Okay. So let's see. Let's look at the corresponding uh, corresponding elbow maximization that we come across, right? So let's see. What is this f of q? This f of q, and I will just write down this definition. So it's q of z log of p of x comma z divided by q of z dz. Okay, this is what our elbow is. Now, again, we have made some approximations for Q of Z, right? This particular approximation. Let's write down that. So what will it become? So this will become product over I, QI, and I will just write down QI. I will uh, just for the sake of brevity, right? For clarity. And the inner thing will become, so this is log of P of x comma z minus log of product of QIs, right? So I have just substituted our approximation in the elbow definition. Okay. Uh, what will this thing become? Uh, what we can do is, so let's say we are optimizing with respect to so I will just write it down. So optimize with respect to QJ. Okay, some J. We are going to maximize the elbow with respect to some QJ. So let us write this expression so that it is easier to judge it in terms of QJ then. Okay. So I will write this thing down as QJ. Okay. And what I will do is I will push everything else inside. Okay. What do I mean by that? So this thing will become what? So you have QJ, then you have product of QI, I not equal to J, ln E x comma z. right? And what else? I will write this thing as dzi. Uh, Let me do this thing. I will split the integrals as well, right? And this is dzj. So what I have done here is I have basically split my integral in two parts. One with respect to the the jth coordinate, right? A jth index qj and zj, and everything else I have pushed inside. So this is only with respect to this first term. So ln pxz remains as it is. You have qi's, you have integral with respect to qi's and the corresponding dz's, right? So it's nothing. It's very simple thing. I have just split my integral. So this integral, so this dz was, I mean, this dz was actually what dz1, dz2, so on till dzm, right? I have just split. So, and this integral was also similar, right? Z1, Z2, so on till something like this. It was like this. So I have just split my integral into two parts, two disjoint part. That's all. This was the first term, right? Corresponding to this ln px comma z. What will be the second term? So this second term, what I can do is similarly. So what I will do is, okay, so this ln product of qi is nothing but what? Summation of log of qi, right? This thing is just this thing because log of product is sum of log, good. And uh, so what will this? Uh, I mean, I hope you will agree that this is nothing but some qj. I mean, so this is like this is like I should change my color. So this is like ln q1 plus ln q2, so on and so forth, right? So like ln qj, some qn, something like this. It's like that. So what I can do is so uh, yeah. So what I will do is I will just take out the jth summand in this term and write that thing down. Okay. So what I should perhaps do is I'll make this thing so that it's clear what is derivation and what is not. So qj and ln qj dzj plus some constant terms, right? What do I mean by that? What are these constant terms? So these constant terms will look something like this, right? So it will be like, let's consider one of these terms, let's say ln q. Consider any general thing, I think. Uh, so it will look something like this. For example, it's like integral product of qi's, right? Product of qi's, and there is ln q1, let's say, and this is so the integral is whole, right? Uh, so in that case, uh, so this will become, so this is like pz, right? Yeah. So what you can do is you can perhaps split this thing similar to what we did here, right? So this will become q1 ln q1 into integral of q, so, and this will have dz1, the q2 dz2, so on till qm dzm, because all of these are disjoint, right? I mean, you can, since there is only one function with that only one term that depends on z1, you can say take that out, similarly take others out, and these all will become one, right? So these all will become one, and hence you will get some, so this constant will look something like, summation of qi ln qi where I is not equal to j, and that is our constant. But that's fine. It is some constant. We are not worried about it right now. So for the time being, we'll just say that that is some constant. Okay. Now what we'll do is uh, maybe I should minimize this. Uh, I'll resize it. Resize. Yes, let's put it here. Okay. So what I am going to do is we are going to so this term that is there inside, right? This let me highlight it. So this term. So we will write a name for this term so that it becomes so it will help us in our uh, calculation. So this term, let's call it let. Uh, so uh, this thing that is product of qi not equal to j, right? Uh, ln p of x comma z dzi, right? This thing we will call this as so this is what? So this is basically your expectation, right? This is your expectation under I not equal to j log of p of x comma z. That is what this is, right? I mean, just by the definition of expectation. And what we will do is we will call this thing as ln of p tilde of x comma zj. So this is how it is defined. So so we are just giving some name to this entire thing because this looks very complicated, right? I mean, to make things simple, we'll say that th- this thing is nothing but your expectation, and we will say that this expectation is equal to this is defined to be like this. That's all. Okay. Once we have defined this thing, the calculation will suddenly become very familiar to us. What will this f of q become? F of q will become integral. So this is qj. This entire thing that is highlighted will become this log of p tilde of x comma zj dzj, right? What was the second term? Second term was nothing but minus qj ln qj dzj, and then there was some constant that we don't care right now. Okay. Now, let's see what this thing is. So this is actually, so if you take out the negative sign from these two terms, this thing is integral qj ln qj over ln p tilde x comma zj dzj plus some constant because why is this constant? Because it doesn't depend on zj, and right now we are just trying to optimize with respect to qj. That's all. So we are only concerned with terms that involve qj, and rest of the things we are not concerned about. Let's see. So, I mean, if you remember, you should immediately recognize. Oh, sorry, it's a blunder here. This is not ln anymore because we took the ln and wrote it like that. So, so if you recall what this term, it will become very. Uh, if you recall things, this is something which is very familiar to us. This is nothing but this is a scale divergence between qj and the p tilde something maybe I should write qj of z, right? And p tilde, let's say maybe p tilde of x comma z. This is what it is. This is your F of Q. Okay. So now it's a very good thing for us because we want to maximize this elbow, right? We can maximize this when this is minimized, right? This has to be minimized. And what is the minimum value of DKL? The minimum value, so and let me write it down. So maximize uh, F of Q is equivalent to minimizing of with respect to Qj perhaps. Qj is equivalent to minimizing DKL between Qj and this P tilde, right? And when will this minimization happen? What is the solution for this minimization? Well, we know that Kale divergence, the minimum value of Kale divergence is zero, and that can only occur when Qj star, let's call it Qj star, right? When this Qj star is equal to this P tilde of x comma zj, right? So this is the solution. So this is the solution of Qj star. And so how was this P tilde defined? So so remember that we didn't define P tilde, we defined log of P tilde. So we will have to take log on both sides, right? So this implies ln of Qj star of Zj is equal to ln of P tilde of x comma Zj. And what was this log? This was this expectation, right? This was expectation of I not equal to j of log of P of x comma z, right? Right. So, uh, right. I mean, yeah. So this is what it was, and then there will be some additional constant, right? Because we want to make sure that this is a distribution and so on and so forth. So, so this is what it boiled down to. Now what we can do is we can simply from here we can simply write down what this Qj star is actually. So the Qj star of this Zj will become what? So we take the exponential on both sides. So this is exponential of expected value of I not equal to j, right? Of log of p of x comma z, right? And what do we do of this constant term? I mean, remember that the constant we should not worry about the constant term because that will just result in a normalizing constant. So normalizing constant will be just integral of the numerator, right? So this is I not equal to j log of p of x comma z dzj. So this is what your this thing looks like. So, so this is the value of your uj star. I mean that you should use to perhaps I mean maximize your elbow with respect to qj. Now, so this is fascinating, right? I mean, remember where we started from? We started from this problem that EM has, and we sort of we were we sort of decided to make an assumption that will simplify our lives, and that thing resulted in this calculation, and finally we got a value of qj star in this closed form, which is actually quite I mean in my opinion it's actually fascinating because you didn't have to do any optimization here, right? You didn't have to do any optimization here, unlike EM algorithm. You got everything in a closed form solution. Now, of course, you will have to do some iterative thing. So what you will basically do is you will start with some assumption on QIs. Maybe assume that all of them are Gaussian, something like that, and then one by one in turns. First you will update Q1 by keeping others constant, then you will update Q2 by keeping rest of them constants, and so on and so forth. So you will perhaps iterate over all of this multiple times. But I mean that will be very easy because you know that each time what is the value of all of these things. So, so this is, I hope that this gives you a flavor of variational inference, right? I mean, so what is, I mean, people often ask that, at least I was very confused that, I mean, what do we mean by calling these things as variational things, right? I mean, why are we calling this as uh, uh, variational inference? I mean, what is variational here? What do we mean by variational here? So, so the thing is, uh, so basically what we are doing here, so this whole optimization is, if you think about it, we were not optimizing on so this optimization was unlike your usual uh, your usual optimization where you optimize on a Euclidean space. If you think about it, we were optimizing with respect to a function here. I mean, Qj star, whatever we obtained here, is not a value, right? It's not a scalar value, it's a function. So this is like a free form. So we were basically doing a optimization. uh, Like we so therefore we wish to make a like a free form optimization on your elbow, right? And this free form optimization on top of functions is what is called what people refer to as variational optimization. Okay, where you are optimizing on top of a function particularly. Okay. So yeah, this is your variational inference. We'll stop this lecture here, and next time we will start with something called VAs, variational or autoencoders, and we will see that how VAs are. Uh, uh, we got a flavor of variational inference by making this mean field approximation or factorized approximation, right? What we will see is that in VAs, we will make another assumption where we will approximate Q of Z with Q of Z given X. Okay. And uh, so that will help us basically in coming up with tractable distributions of Q of Z. And yeah, we will see what happens. Okay. So yeah, that's that for this lecture. Uh, and thank you. And yeah, I'll stop the recording.